Alright, I'm glad you're still with me for the example part of this video. So let's begin with some examples. So this is number 24 in the textbook. And the example says that we're going to integrate x squared minus x plus 6 over x to the third plus 3x. The first thing we have to ask ourselves is it a proper rational function? That is the degree of the numerator less than the degree of the denominator? And the answer is yes. 2 is smaller than 3, so we can continue. Now we need to factor the denominator into linear terms and irreducible quadratic terms. It isn't hard to see that x squared plus 3 is irreducible because b squared minus 4ac is negative. I think it's negative 6. So right now we are in the position of being able to write down the partial fraction decomposition of this function. I'm going to do that separately because I like to keep it off to the side. I don't want to constantly be working inside the integral. So I'm going to put the partial fraction step over here. X squared minus x plus 6 over x times x squared plus 3. Well, that's going to decompose as a over x, that is a linear term, plus bx plus c over x squared plus 3, which is the partial fraction that you get for irreducible quadratics. If I multiply through by the denominator to clear everything out, I end up with x squared minus x plus 6 is equal to a times x squared plus 3 plus bx plus c times x. So I've cleared denominators. Now I'm going to multiply everything out on the right-hand side so I can build my point of comparison. X squared minus x plus 6 is equal to ax squared plus 3a plus bx squared plus cx. If I sort things out into like terms, x squared minus x plus 6 is equal to, okay, so I see an a and a b stuck to the x squared, and I see a c stuck to the x, and I see a 3a as my only constant. Now I'm positioned to make the comparisons that I need. 3a is equal to 6 because those are the coefficients, the constant coefficients that I see. So my system of equations is going to say that 3a is the same as 6. That's easy to solve. That c is equal to negative 1. So c is negative 1. And then finally that a plus b is equal to 1. That the a plus b I see here is equal to the 1 that's in front of the x squared. Well, I know a is 2. And so that means that negative 1 is equal to b. So that tells me that I can rewrite this complicated integral as the following. This is equal to the integral of 2 over x, because a was 2, plus, okay, so b is negative 1 and c is negative 1. And now I can split this up into 3 different integrals. This is 2 times the natural log of x. This integral turns out to be a u substitution, where you let u be equal to x squared plus 3, and so that du is equal to 2x dx. And what you'll get when you do that is the natural log of x squared plus 3, but with a 1/2 stuck in the front. For the last integral, we're looking at an arctangent. And it's going to turn out to be that this is 1 over the square root of 3 times the arctangent of x over the square root of 3. And that has to do with the fact that the a squared in the form is root 3, or that a squared is 3, and so a is root 3. For our final example, let's look at a function where we have to use long division first because the rational function is improper. So this is improper because the degree of the numerator is 5. The degree of the numerator is bigger than the degree of the denominator. Degree 5 versus degree 3. So I can't even proceed in this problem until I've reduced it by using polynomial long division. So x to the third plus 1 divides into x to the fifth plus 0x to the fourth plus 0x to the third plus 0x squared minus x minus 1. What's going to give me x to the fifth if I multiply by x squared, or x to the third, is x squared. X squared times x to the third is x to the fifth. X squared times 1 is x squared. Now subtract. 0, 0, 0. 0 minus 1 is negative x squared, negative x, negative 1. Now, the degree of all of this is smaller than the degree of this, and so I'm finished. The remainder is done. I can go no further because there's no polynomial I can multiply x to the third by to get x squared out the other side. As soon as you get to a smaller degree than the denominator of your original fraction, you can quit. What does that say about f? Well, what it says is that x to the fifth minus x minus 1 over x to the third plus 1 was really secretly x squared plus the rational function given by minus x squared minus x minus 1 over x to the third plus 1. That is the remainder divided by the divisor. This is the first reduction we have in the problem. We go from an improper rational function to a polynomial, which I know how to integrate, plus a proper rational function. And this thing you can use partial fractions on after you factor it. So let's factor. In the denominator, we're going to get x plus 1. Here I'm just using the difference of cubes formula. So this is a partial fraction problem. And this is just the integral of a polynomial. So if I want to do my partial fraction step, I would write down minus x squared minus x minus 1 over x plus 1, x squared minus x plus 1 is equal to a over x plus 1 plus bx plus c over x squared minus x plus 1. And then we proceed from here. So I'll finish this problem up in the notes, but from this point forward, it's about finding the a, b, and c, and then using techniques that we developed in section 7.2 and section 7.3.